All right. I will keep this brief because I'm not the feature attraction and I'm not a particularly good warm-up act. Um, the person you're going to hear from here this afternoon or morning, depending upon your time zone, is named Erik. He works for a company called HTNB. His office is in New York City. I've seen it. It's a real place. It is not a fiction. Um, Erik has a special affinity for bridges. I don't know if he was born that way, but he sure like, lives and breathes it now. And he has some really interesting stories to tell. And I've had the good fortune of being able to enjoy quite a number of those. And what he's going to talk about today is sort of this intersection between his work in engineering, particularly with a focus on bridges, and the use of NOAA data and information, particularly precipitation data, and how those two really relate to one another. It's really interesting work, and I think I'll just leave it at that and give you the floor, Erik. It's all yours.
All right, thank you so much, Russ. And thank you everyone today for all your time and attention. I have always had an affinity for bridges. I used to build the connects bridges across my house, so I guess I was born to be a bridge engineer. As I've gotten to know a number of people from NOAA, I realize that many of them have a specific moment in time, an event that occurred early in their life that made them deeply interested in the intersection of weather and something else. And so I figured I would start off by talking about what my key event was, and it's shown right here on the screen. This is actually a local news story. A local news journalist took this picture. It was front page news when Hurricane Ida went through New York in 2021. And as luck would have it, there I am standing more or less center stage on top of a failed culvert that impacted tens of thousands of commuters at these railroads. And so me being deployed as an emergency bridge inspector to this site to try to evaluate, obviously, the damage as people walk below rail lines where gravel had just been. And it really was a microcosm for what it means, what this extreme weather aspects mean for transportation infrastructure. It was unfortunately a perfect microcosm. It was the fact we saw that very real damage from extreme weather. We saw this was a hidden vulnerability. This culvert had been in service for more than 100 years with no issues. And suddenly this is the time that it becomes vulnerable and fails. And number three, cascading impacts, where this 12 or so foot span and its failure ended up leaving tens of thousands of people unable to get to work. And so leaving this site, I really couldn't think of myself as anything other than a bridge engineer now on a mission to try to understand and quantify bridges and how they interact with extreme weather data. As of course, NOAA was the place to go. And I've been very grateful for all the NOAA contacts that I've gotten so far and all of their inputs. They've been able to help me think through this problem. And so let's see. Today's discussion will really have sort of three parts. One will be the data that I'm using and also the way that I'm trying to transform it through a cloud-hosted pipeline on my own to better understand it and better tailor it towards bridges. We'll also talk a little bit about the way that I've been partnering with those from NOAA on ways to expand this methodology. The purpose and how we're able to, once we have this methodology in hand, quantify risk to bridges in ways that it hasn't happened previously. And number three, the ways we've been able to communicate this to different stakeholders and what this means to our industry as a whole. And so just a little bit more background on myself. So I'm now celebrating 15 years at HTNB. I've been fortunate enough to serve as a designer of bridges, an inspector of bridges. I've worked during the construction phase, being out in the field, helping them to be constructed, and then also serving to close out some of the major projects in our country. And just a little bit more about HTNB. Most people have not heard of it who are outside the transportation space, but it is a firm of about 7,000 people. And we work closely with many DOTs, Departments of Transportation. And we also are the ones oftentimes who are signing and sealing and putting our professional engineering stamp on drawings for bridges as they're created. And so this really summarizes my key, sort of my conventional background, but I also have this other background as well. And that is that I serve as HTNB's bridge technology lead, which has brought me to contact with data from all over the industry and how it relates to bridges. This is me on the Kosciuszko Bridge in Brooklyn, measuring cable forces, bridge resiliency and extreme weather, which we'll talk about today, partnering with different freight entities, trying to understand the impacts of freight on bridges. And so I also offer this disclaimer, which is I don't have formal expertise in any of these topics that are bulleted there. Data science, climate science, GIS, numerous other areas. And yet to truly understand the impacts of extreme weather on bridges, I've had to get to know the people in these spaces and the areas of these well enough to interact with them. And so this really speaks, I think, to the multifaceted nature, the multidisciplinary nature of some of these most complex challenges that we're facing. And so before I jump in, I just want to step back and talk a little bit about the engineering mindset. This is sort of the signature figure that engineers think about. We have a distribution of how much load will be applied to our structures, be it rainfall, be it a heavy truck, and then similarly a curve of how strong that structure is or that structural element is. This is really the go-to figure that we use to understand. We're trying to minimize the failure region, of course. And so as our industry, many of our structures are reaching the end of their useful life. This strength curve is moving to the left. And as our loads become greater, our weather becomes more extreme, this curve is either moving to the right or this tail down here is getting fatter. And so it's really critical for us to understand how these two curves shape out. And doing that with data and in partnership with different agencies like NOAA has become really important. And so just to step, in all my interactions with various meteorologists and climate scientists, I've been forced to sort of articulate the engineering mindset in a way that I really never had to think about before. But to summarize all of engineering, in a few bullets, there's a deep level of trust in the code, although things are changing much faster than the code can keep up with. And for certain types of risks, engineers are very focused on what is the specific design criteria and limits. And don't give a whole lot of thought sometimes to what is beyond those extreme tail events. Most engineers, although this is changing, don't have deep knowledge in data or programming, although many engineers now coming out of school do. And then also, people looking back at the last 40 years, things have been relatively unchanged. I have every reason to believe that will not be the case in the next coming 40 years. And so for that reason, we really need to be smart about the way that we approach these problems and use the best available data sets. And so the transportation sector, I'll try to summarize it. I'd say always be leery of someone who's trying to summarize $1 trillion industry in a single slide, but I'll take a quick stab at that. Transportation, just like many industries, if you're not thinking about us at all, we're doing our job. It's only when we have problems that people end up thinking a lot about transportation. One of the biggest challenges facing the transportation industry is extreme weather. This really is one of the biggest deltas we're facing in the coming decades. DOT, Department of Transportation, probably obvious. The thing that is most critical to understand about transportation space is that we have tens of thousands, hundreds of thousands, really, assets that are currently out there. And so while finding the best possible design criteria, understanding what our code should be for the future is critically important, we also have to remember that many agencies are forced to deal with existing assets from decades past that were not designed to those, and be as wise as possible with limited funds to bring those up to the nearest possible amount of strength. They have a widely distributed system. So if you're a property owner and you're really crossing your fingers, you don't see a 100 or a 200-year storm at your property, that is one thing. However, for transportation agencies that cover an entire state, they have such a wide distribution, they're almost certain from a cumulative probability perspective to get hit somewhere on their system. And so there are new strategies we're seeing evolving that really could be a game changer for that. And then finally, there's a very complicated recovery process, both on the policy side, as well as just the physical aspects of building back a system after there is widespread damage. And so I deeply believe that for our sector, the best path forward will be informed by the data that all of you provide and have been collecting and continuing to collect. And so to zoom back in, this will sort of be a thread throughout, is this event that I responded to, and also sort of my journey from that point, from sort of looking dazed and confused on this bridge, to now having at least my own methodology to try to think through more holistically this risk to bridges. And so zooming back in from 30,000 feet, I set out on a quest to understand data and precipitation data. NOAA obviously has, I think, dozens of precipitation data sets, it's fair to say. Some of them are timestamps to older, are no longer currently up to date. Some of them were difficult to access or to manipulate. Some of them were in file formats that I didn't really understand or couldn't deal with. And so it was a challenge initially to really figure out which data sets I should be using. And so I should also add that the seeds of everything I'm going to show you today were planted by an intern from Notre Dame, who actually was able to find a way through with a Python API, get access to data, start plotting it. And that really showed me the level of connectivity we could gain through all of this by using programming methods. And so never underestimate an intern who knows Python and also has something to prove. It was truly the moment that I got traction when I came into interactions with the NOD program from NOAA. This is a systematic effort to put various types of data onto the cloud so they can be accessed in a secure, repeatable, and programmatic way that allows me to grab that data immediately. This is actually a slide that someone from the NOD team gave me. They have much cooler graphics and things that move that I don't have, so they're showing me up in my own presentation with some of these graphics. But all that to say, the NOD program, I wouldn't be here if it weren't for the NOD program, because I wasn't able to get access to data at a scale, at a reliability, and an efficiency otherwise through this system. And so I settled upon the multi-radar, multi-sensor data set. That's the one that all the work that I'll be showing today is what I'll be using. This takes the best from both rain gauges and radar towers. It integrates them into a single data set that is provided as rainfall accumulation for the continental US. It's provided on an hourly basis of what rainfall was accumulated for that past hour. And it's approximately a square mile grid that is shown in near real time. And so besides being accessible via NOD, which is shown on the left, it's also accessible on a viewer, this operational viewer here. And that's where the QR code takes you, is to that operational viewer. And I was using the multi-sensor data pass2 has been primarily what I'll be using and showing and walking through today. And so as a bridge engineer, finding these accumulation files for rainfall was a true game changer. It was allowed me to look at events like this one here in Indiana that caused this bridge washout and go back and see what did the data show. And what it actually showed is on the left here. This is not our radar file. This is a colorized rainfall accumulation file. So that the 10 inches here of this red dot represents 10 inches of rain, 2 inches beyond the 1,000-year storm. But I think what stands out for me most is not the extreme nature of that event. It's not the bridge washout, but it's the extreme isolation of this event. It's the 24-hour amount of time. Is that if we didn't have a rain gauge, and there, to my knowledge, there was not a rain gauge nearby, this event would have actually not been captured at all in a quantitative way, but for the MRMS data set and the value that we're able to achieve. And so while events like Helene, that many of you just lived through and witnessed, are really these massive hurricanes are systems that everyone pays attention to. It's kind of like knocking the dartboard off the wall. Events like the microbursts like this one here are like a single dart on the dartboard. It's nearly impossible to predict in any amount of time ahead of time where these will occur. And therefore strengthening infrastructure to prepare for them is very, very difficult. And so quantifying how often these are happening and where they're happening is something that I've been able to do more holistically with the methodology that I provided. And many DOTs aren't aware of this MRMS data set. It's something I'm trying to change with different presentations that I give, but speaking to letting them know about this so they're not reliant upon widely distributed rain gauges, but can in real time or near real time see these types of events. And so now we sort of zoom in on the core methodology that I had today. And so, I know I've covered quite a bit of ground already, and I'm just getting started, but this is the part of actually the innovation that I was able to push forward, and the reason I've been interacting so much with various folks from around NOAA. Is that I took those GIS files available through NOD, which was rainfall accumulation over time that was shown. And I took 27,000 hours worth of those data, and I queried them via NOD. I put them into a Python environment, and then I put them into a massive tabular database. I then was able to query that database for individual locations. Here we see the state of Massachusetts with every single bridge in Massachusetts shown as a blue dot. Well, it's hard to see. And so I queried those 27,000 hours of time against the various locations we have and came up with an hourly time history for every single bridge location. While this is a vast simplification, this is essentially a virtual rain gauge at every single bridge. And so just to show this a little bit differently, but really the same idea, is that I was able to take these plates worth of data that NOAA provides as rainfall accumulation, put them all, 27,000 hours, which is multiple years worth, into a database that is actually maintained on an ongoing basis, and then query them for individual points and locations to get the hour by hour time history for locations that I cared about. And so this will only resonate with a handful of you, I assume, but I did want to give a little bit of background on the specific methodology that I've been using. I'm taking the GRIB2 files in a zipped format and downloading them, and then unzipping them and converting them into NetCDF files, at which point I query them for a number of factors and then compile them into a Parquet file, I'm able to then partition that and store that on an S3 bucket. From there, I have another dedicated script that can go through, enter certain parameters like the date range, as well as the specific latitude and longitude, and it returns in a specific format the data for that location, so you can create an hourly time history. And so this allows us to do a number of things that we really wouldn't be able to do otherwise. One of them is to understand the various maximum peaks for different durations. So this data was taken from Helene. Actually, it's the entire year 2024, but of course the spikes here at the end of September were Hurricane Helene, and it's a bridge that was unfortunately washed out in Asheville. And I think showing the data in this way is not only is possible by what I'm working on, but it also has a number of value, because if you wanted to understand, so let's say the 3-hour peak, what was the maximum 3-hour time frame that was witnessed at that bridge site? This allows you to quickly look at that amount and quantify it. Whereas the only way, at least that I'm aware of with the operational viewer, to obtain that would be to flip through hour by hour and hover over that point to get the 3-hour rainfall. So this allows you to, at scale and programmatically, identify the peaks that occur. Another thing we were able to do is to query, again, for every bridge in the state of North Carolina, and put that into an ArcGIS, or actually a Power BI file that hosts ArcGIS within it. And while this is a static image, it does allow us to query for things like the amount of rainfall that fell. We can look at different durations. We can filter by different date ranges, and even hover over specific bridges to see which bridge it is and what was the maximum rainfall that was observed. And now it's probably time just for a brief disclaimer. Nothing I'm showing today is a formal product offered by my company. Everything I'm doing today is a preliminary research effort. Our goal really has been to, number one, verify that we can understand this data and transform it at scale, meaning for the continental US for multiple years. And the second thing is to demonstrate the value the data has if we're able to do this transform. What are the things we can take away? So everything I'm showing today is preliminary. Nothing I'm showing is a formal product that we offer to date. This is simply exploratory and trying to understand and quantify where rainfall weather and rainfall data can interface with bridges more holistically to help us inform to make the best choices for the future. And so, my core motivation here was not so much to make a cool dashboard. It was really to understand and quantify the risk that is faced by a population of bridges. Now, of course, I'm geared towards bridges and rainfall is what I'll be talking about today, but I also wonder, what other types of events do we have granular data for? What other groups of assets? Is it utility lines? Is it railways that we could also do something similar for in this manner? And so the typical play when you're dealing with this type of data is to put it into a histogram. And so this shows all 18,000 or so bridges in the state of North Carolina, and it shows the peak 1-hour rainfall that fell, in this case, in the year 2021, and we're showing its histogram. So this is the first way that I showed the data that I was able to gain. And the challenge there is that this tiny little sliver that's hard to even see shows that we have a few tail events that barely even register, but they exist. And so the second thing that I tried to do was a graphic like this, where I took every single bridge in the state, again, around 18,000 of them. I put them in with every bridge being a dot. And I put on the vertical axis here, the total amount of rainfall that fell. And on the horizontal axis, I placed the bridges in essentially arbitrary order. It's like this dot up here, this bridge, this one saw 3.5 inches of rainfall. This one over here saw maybe 3.2 or 3.3 inches of rainfall. And so sort of fixating on this graphic here, I have it on the next slide, the identical graphic. This is the same data that was in the histogram. It's just shown differently because every bridge individually is represented. And so the next thing I did was I took all this data and I put it into ascending order by bridges. And while it's sort of turned to 90 degrees, this is essentially an extreme value distribution for all the bridges in the state. And we're seeing something that really wasn't well quantified before because we just didn't have the coverage by rain gauges, is the vast extremes we're seeing with these top handful of bridges, these top couple dozen bridges, seeing so much more rainfall as a peak than the rest of the population, or at least the median average of what the rest of the population saw. The challenge becomes this last 1% or so of bridges, we have no meaningful way to predict year to year which bridges will see that 1%, which means there's a great challenge in trying to understand where dollars should be spent to make bridges stronger and retrofit them, because we have no meaningful way to predict where this will be. And so this is the data from North Carolina through the end of September, so including Helene. And this magenta color is shows all the year for 2024. So again, 18,000 bridges, the peak, in this case, 24-hour rainfall was seen for every single bridge in a state. Like this bridge, for instance, saw nearly 19 inches of rain, and you can see the extremes. And you can also look at, for the entire population of bridges, how much more rainfall was seen in 2024 as compared to the other 3 years that we have currently have data for within the MRMS set. And so because Atlas 14, which is the, which defines the 100-year storm, can be found for every individual bridge in the state and map to them, I did that and was able to show the percent exceedance of the 24-hour 100-year storm for every single bridge. And we see that, hundreds of bridges exceeded that 24. It looks like about 1,200 bridges in 2024 exceeded their 100-year storm. And that's in comparison to a total of 7 bridges over the previous 3 years exceeded their 100-year storms, at least by the metrics that I'm using. And so now I have just a few case studies of other ways we're looking at this data and trying to understand how it can be valuable. One of which, and this is feedback I got from a number of hydrologists, was, it's fine to know what happened at the bridge, but a bridge and its hydraulic stability is really defined by what happened within the watershed as a whole. And so what we were able to do is use the USGS stream stats program, find for a specific latitude, longitude, the boundary of that watershed, and only grab the points that are within that watershed, the grid points shown here, and then quantify those and average them. So this is a way that it could interface more holistically with hydrologists and their concern. And I should mention too that, at least anecdotally and by some studies that we found, bridges of certain types of watershed sizes are much more vulnerable to different types of events. If you have a small watershed like the one that I responded to after Hurricane Ida, it's really a 1 or 2 mile watershed is very vulnerable to the 1 and the 3 hour duration peak storms, whereas a slow amount of rainfall over 24 hours may not affect it all that much. Larger rivers, of course, are more affected by something like a 24-hour event. This is a use case we're just starting to think through. This is the USGS landslide dashboard that was put together after Hurricane Helene alongside several other agencies. The QR code takes you there. It's hosted within ArcGIS. And we're just thinking through now, what if we had point location rainfall data for each of these sites? What could we do, or could we do better forensics on trying to understand the events that occurred and help us better plan for risk in the future? Again, not something we've done, but trying to look at ways that point location hourly rainfall data could augment other analyses that are ongoing. And my last example is looking at the operational side of roadways. DOTs have the unenviable task of being responsible for data, or for being responsible for roadways that are spread out across, in some cases, thousands of miles. And so they have to do their best to understand and mitigate challenges along those roadways. And so what I've done here is taken about 100 different points, spot checked against I-70 between Columbia and St. Louis. And this is a storm that happened about 2 years ago, 2.5 years ago. And we were able to look at the hourly rainfall for every single point for a multi-hour period and create this heat map. So the interstate distance is shown on the horizontal axis, time is shown on the Y, and you can create a heat map of the intensities that were shown. Again, this is very preliminary, but this idea of, can we use these point location checks to allow us to more holistically understand extreme weather as it occurs? And so, of course, NOAA is putting together Atlas 15. I think I'm the most excited person in the whole transportation sector to see Atlas 15. I've already started looking into the pilot project that was launched, and I think this is a really good step forward for the industry to better understand and quantify risk. But again, we had that challenge that so many of our assets were built to Atlas 14 or even before Atlas 14, as many of them are decades and decades old. And so with better design criteria helps us to understand and quantify risk, we still have an existing asset problem. And so I'll close today just by saying a few things, a few questions that really come to mind and things that I've heard from others in the transportation space. The first of which is how can transportation agencies use this new data and this newly available data set? I think one thing is we can look at forensics. This is an event that occurred in the Northeast where we grabbed the peak rainfall for 3 hours, 3 hour duration for different bridges in this region. Found that some of them exceeded almost met 7 inches of rain in 3 hours. It exceeded the 100-year storm. And then only a few miles away by our analytics, we didn't even exceed a 100-year storm. And so if you're able to get much more location-specific data to look at this, I think that could change the way that we look at forensics. But it also brings to bear another idea for me, which is if I can find the extreme rainfall that occurred and bridges that failed, can I look at places where that same extreme rainfall occurred, but the bridges survived? And to more holistically look back at what bridges saw demands well in exceedance of what they were designed for, but still survived, we can start to ask the question, are there types of structures, are there classes of bridges that are systematically outperforming the rest of the population? And is replicating more of those types of bridges something we should be thinking about as a way forward with design? And so I think there's a natural inclination among the engineering community to try to pair all of these inputs with the causality aspect of it. Can we look at what were the inputs of that site, what were the slopes, the type of soil, the width of the bridge, width of the river, and the rainfall, and try to predict where failures will happen in the future? And that's really challenging for two different reasons. Number one, sites are always changing. Rivers move, bridges change, a tree could fall over the river. There's a lot of parameters that are very hard to understand and quantify. The second thing is that for many of these extreme events, for instance, 7 inches of rain in 3 hours, overwhelms just about every system. So again, this is the dart on the dartboard. We have no idea when it's coming. We have no idea where it will happen, at least a few days or weeks out. We don't have a way to predict that. And so this challenge of how can we make everything strong enough when these events can happen pretty much anywhere in the country. The second thing is, can our standards and codes keep pace with this rapidly evolving environment? I think that codes are absolutely doing their best. There's a number of agencies working hard to move codes to the place they should be, and also advise on future projections, Atlas 15 being one of them. But there's also this paradigm of, and this is a graphic from, actually predates my practicing career from 2008, but it shows this idea of, is our curve shifting? What does that mean on the demand curve? I think, the science is obviously indisputable on shifting curves. However, we do have this other idea of what if our tails are getting fatter? And so while an incremental shift in the curve, at least in the current time frame, has deep implications, the fattening of our curves at the most extreme events, the events that we care about, the ones that we think of when we think of extreme weather, if there's a steep increase in the amount of extreme events that happens, that's challenging for two reasons. Number one, these are events that cause, by and large, the larger amount of data of damage. And number two, we have the least amount of data in this very small portion. And in some cases, thinking about things like uncertainty intervals, we actually chop off our tails in some cases because we don't have enough data there to statistically speak to it. And yet these are the events that happen. And so looking at something like bridge specifics and looking across an entire state allows us to at least better understand what those tails look like. And then finally, what about our existing assets, which I've mentioned a number of times? This is really the air. This is the challenge that we have in the transportation space. This is the most near and dear issue to many transportation agencies, is that no matter how good our design criteria becomes, we have it can be a challenge to predict and understand what those will be. This one's shown from Hurricane Harvey, which was just well beyond the 1,000-year storm for many locations, and just overwhelmed a number of assets, only one of them shown here. And so I think it begs the question, what does a resilient strategy look like moving forward? And how can we as engineers plan for this when we simply can't make everything strong enough to withstand well beyond a 1,000-year storm for every duration of time? What does our strategy look like? And so I'll close today with this slide here. And my example has been rainfall and granular data. I feel like making these taking high precision data sets and turning them into site-specific locations could yield advantage on a number of industries. And so we really tried to approach it with these three buckets at HTNB as part of our resilient infrastructure solutions. And this is something, these three buckets really follow the language from IIJA on resilience. So the first thing we're trying to do is to prepare better by understanding this data and by looking at ways we can better quantify it and think through strategies. Second thing is we're trying to adapt our bridges to make them more resilient. In some cases, we have times when planners say, because of the alignment of that bridge, it will get overtopped and during a 200-year event, let's say. And we want to understand as bridge engineers, how strong do we have to make that bridge so that it can be overtopped? This is, of course, a little model bridge in a flume, but we see water floating over that bridge. And so we're using models like this to understand what the demands will be in these use cases. It's not just closure of that road, it's actually understanding what are the fluid dynamics that affect that bridge. And then finally, looking at ways we can more rapidly respond to these types of events. I started off with kind of a bummer here, right? A railroad bridge washed out, people walking below gravel. But this story actually has a relatively good outcome, which is that after this event occurred, we worked closely with the railroad and their contractors. And only 6 weeks after the contractor signed on, we had this trains running on this permanent structure that should last somewhere around 80 years that happens. And so as a bridge engineer facing the challenge of, I'm not sure I can design something strong enough and replicate it across an entire inventory of assets, I believe we have to start looking at additional strategies to make things more resilient and to also allow us to replace them wherever the damage occurs and be more agile in the responses that we create, and letting NOAA's data that's being provided help us to make those decisions and those arguments better. Thank you.
Wow, Erik, thanks. That's quite a lot that you have shared. Going all the way from identifying precipitation data to how to access it, then to getting into your space of bridge engineering and analysis. And I think the agility with how quickly you were able to analyze Helene-specific precipitation regarding and during the event is what catches me amongst the many different parts that you've shared. It's pretty tremendous from many different lenses. Yeah, go ahead.
That sort of speaks to our previous conversation, Jenny. I think it's probably a point worth making, which is there's really sort of two major areas of value here. There's the short-term aspect of being able to use the MRMS data to look at locations of interest and to be able to react in near real time. The past 2 data is up and posted within about 2 hours after that raindrop hits the ground. And so there really is a short-term benefit for better situational awareness during and then immediately after the storm. And there's also the other aspect, a lot more longer-term location or longer-term way of thinking about this, which is trying to plan for the future and the path forward. So I think those are usually different groups look at those 2 challenges. But I think this methodology, and of course the data being provided by NOAA through MRMS, through NOD, really speaks to both of those challenges.
Yeah. Imagining the day in life of a structural engineer with a dashboard where they can view near real time precipitation data coming in, watching historical behavior of that bridge and what it's designed for in the threshold, and having the alerting mechanism. That's really the key component here of the many different things you've shared. So for the group here that's listening, thank you for taking the time to listen to Erik's talk. I think there's a lot of connections here at NOAA across a number of different NOAA programs, and also with NCEI as it's making program and data product development efforts under the industry proving grounds. So at this point, I invite everyone to raise questions, raise your hand, or please leave notes and thoughts and comments in the chat feature. This is a time for you all to ask questions or ask anything you would like. And I see that there's one. So while others are thinking about what they'd like to ask, and Erik, I'm going to read you one comment or question. This is coming from Noah Nelson. Hi, Erik, great presentation. Is there a single data set containing the design criteria, i.e. the designed 100-year or 1,000-year storm rainfall discharge for various infrastructure, for example, bridges across the United States?
Yep, that's a great question. So, and it's a multi-pronged answer for better or worse. And so, of course, there's the NOAA Atlas 14 program, which will be updated to NOAA Atlas 15. That speaks to the probability of exceedance for a specific storm. So it could be, let's say, for a specific point in the US, the 24-hour storm over 100 years would be maybe 5 inches, let's say. And that means there's a 1% chance, a 1 in 100 chance of that being exceeded. There's also the FEMA flood maps that have been put together, and that speaks to what is the 1 in 100 chance that flood levels will rise to a specific location, and those are all publicly available as well. There's a number of other agencies that have worked together to create things like exceedance flow of rainfall or of a river that is based to a sort of probability perspective. The challenge becomes that for transportation especially, there are, of course, federal guidelines, there are state guidelines, there are sometimes local jurisdictions, and even project-specific guidelines. And so it's up to transportation agencies to acknowledge and understand the federal guidance, but then make decisions for themselves and have standard guidance across the board for everyone designing within their jurisdiction. And they get to select, in many cases, should there be a more stringent design storm, design flow, FEMA flood map year return period that will be designed to. So really, it's very location specific, but there are a number of sort of interlocking pieces that speak to the demands for a structure.
So short answer is multiple data sets containing design criteria, but we would like for there to be a single source of reference, but we have some ways to go to get there, just given the complexity of how data is collected and organized and made available from different agencies. But I think the two that you referenced, Atlas 14, and then the very soon to be available Atlas 15 dataset and the FEMA flood maps. Okay, thank you. All right, there's another question in the chat coming from Natalie Lerma. How are you considering other factors that may be contributing to how precipitation is compromising the integrity of the bridge? Sometimes these rainfall values aren't experiencing non-stationarity, but when coupled with land use, it changes and is amplified. So in other words, what's the role of land use changes as it impacts the bridges?
Yeah, and maybe one important disclaimer that I should have made earlier on is that I'm not, or I have not to date been directly involved with hydrology and risk assessments. My task primarily has been before the rainfall hits the ground, raindrop hits the ground. And so while I've worked with a number of hydrologists, I've conveyed my methodology, I've gotten feedback and input from them, some of which has been incorporated. I haven't dealt specifically with pairing the extremes that I'm seeing on the rainfall side to specifics of risk and bridges. I will say that, of course, land use and the quickness with which water can reach a bridge is a huge factor in increasing the risk. And that's one of those site factors that is harder to quantify at scale, meaning at thousands of bridges. And if I showed North Carolina with 18,000 bridges, as things happen and the state is developed, it's very difficult to understand, quantify, and analyze land use around all 18,000 of those bridges, of course. And also this ability to look at bridges the way that the guidance from federal highways has been to identify bridges that are called scour critical. And this means they are particularly vulnerable to adverse events during a major rainfall or major river increase. And so that is a way that we sort of group and rank all of the data. And that is something that's available across the board for every bridge. If you look at the National Bridge Inventory, there is a parameter, one of 127 parameters provided for that bridge that shows a scour criticality. So that is something that DOTs look at, they maintain through their inspectors, and they use to prioritize both response, plans of action, retrofits, and also more increased evaluations.
So you highlighted another source, which is the National Bridge Inventory, and that's the NBI under the Federal Highway Administration. Can I copy and paste the link and make sure that that is what you're referring to? So for others that are part of IPG under Architecture and Engineering, this is another stakeholder that would be interested in the new IPG data products. Okay.
And I'm not sure which link that is. That's probably the right one, but there was also, they basically made a user interface on top of their NBI data, and that's called the Long-Term Bridge Performance Program, LTBP. And so that allows you to look at a map of the entire country. You can zoom in or sort for specific states, and you can even query and get a tabular database of all of those bridges. And so while bridges are only one small subset of the entire transportation network, we do have relatively holistic data on those, and many DOTs are taking forward action steps to, in a similar manner, quantify their, we call them ancillary structures, things like culverts, light poles, guardrails, retaining walls, everything else. And so as DOTs and different agencies become much more engaged on collecting data, as they have in the past numerous years, we now can again pair the demand data we're getting from the NOAA side of things with specific assets. And something that Jenny and I were talking about previously, and I think that if anybody could fact check me on this, probably they'd be on this call, but at least as I understand it, the ability to look at a combined algorithm of rain gauges and NexRad data to view it within nearly only 2-hour delay and to get it via the cloud is a level of connectivity to granular rainfall data that even the best data scientists and climate scientists in the world wouldn't have had 5 or 10 years ago. And yet now anyone with an internet connection and Python can access and understand that data. So it's just huge advances being made all around us as a bridge industry and as a transportation sector. And I've just been very grateful to everything NOAA is doing to make those possible. And the various interactions I've had with the Severe Storms Laboratory, with NOD, with IPG to help me better understand these areas.
Thanks, Eric. I am going to leave links here in the chat for both the NOD program and the IPG program, but it looks like there's 2 more questions, so let's get to those first. This one's coming from Jian. Hi, Eric. Are the bridge damages mainly due to intense rainfall locally at the bridges, or are they due to heavy rainfalls from the watershed upstream?
So it really varies by size of bridge and by size of watershed. There's one bridge in the Midwest that collapsed, and the event at the bridge was something like a 2-year event. And yet upstream about 75 miles was a 1,000-year event. And so we see for very large rivers, it really matters what is the full day's worth of rainfall and what happened within that tributary area. For smaller bridges like the one that I responded to, the one that's shown on the top right there, this was maybe a 1 or 2 mile watershed. It was a 200-year storm for the amount of time that we saw. And so just understanding and getting better clarity on what types of rainfall is happening both at bridges, at small watersheds, and at larger watersheds will hopefully allow us to better plan and understand in real time which bridges are probably at greatest risk and also which ones are most vulnerable to events as they occur in the future.
So to the previous question raised by Natalie, she has a follow-up, and she says, I have a follow-up. Debris can lodge in between bridge piers. I think you may have mentioned this, but for clarification, is there another consideration? She may have to unmute. Natalie, if you're online, I'm wondering if you can unmute and clarify.
Yeah, sorry, I think it was a follow-up to Jian, actually. So I was just
Okay.
wondering if they were considering rainfall upstream. And so I was just wondering if debris is also something that y'all consider for heavier rainfall events. I know in Texas, this is usually a big issue in the Brazos River, lodging into bridge piers. And so just curious.
Yeah, absolutely. Settlement or when debris is removed from the shore, be it a tree that falls or something else, that is a serious concern. It's also an extremely challenging thing for bridge engineers and transportation agencies to quantify and plan for. We see a lot out west where there will be a wildfire that will take away all of the soil and brush, so water moves more quickly. It's more able to wash down things like rocks and trees. And then that becomes a secondary factor after a major rainfall that there's now debris in the bridge. There is some body of work around how do we plan for debris at bridges. But again, because of the multivariate nature of we don't know what debris, how fast the water's moving, there's so many things to consider. It really is hard to compile guidance on that. Although, like I said, there is some work that has been done and is currently being done.
Okay, 2 more questions. So sounds like this has been a great discussion. Thank you, Natalie. Get a thumbs up, Eric. All right, this one's coming from my colleague, Jack Settlemeyer, who is part of not only the NOD team, but also the National Weather Service. And Jack says, you mentioned 18,000 bridges in just North Carolina. Just curious, what is the tally nationwide? Let you answer that first.
For the National Bridge Inventory data at 620,000 bridges in the country. There is some nuance there of if they're DOT bridges or city bridges or rail bridges over roadways, but the current tally is around 620,000 for the country.
So I can imagine when you're looking at sort of a national climate resilience strategy for infrastructure, bridges specifically, having cloud-based access would help facilitate some of that analysis.
Absolutely.
All right, so follow up to Jack's question. Second, he says, is the dashboard you referenced live? That is, could one look at it now and see a graphic like the one on the far showing the rolling 1 to 24-hour rainfall at bridges over a user selectable geography to cross-reference with radar loops? So now Jack's talking, and I'm hoping Steve Ansari is also listening because we just had this discussion yesterday.
Yeah, so that is ongoing conversations I've been having with Jenny and others about ways that we can take the workflow that I've created, which is going from the MRMS GIS files all the way to a point location data, and make that publicly available so that anyone can query those locations building tools on top of that, I think there's so many tools that could be built. One would be a dashboard that actually shows asset by asset on a map. Another would be a rolling parameter like this one shown on the left here. But you could query for dates. I haven't even thought of that, of making that sort of live where you could actually query for a specific storm or time period. And so, you know, to my knowledge, none of this is live and publicly available yet. But those are the conversations we're currently having as far as ways we can add value to both the transportation sector, but also many other user communities that would want access to this data and don't have a programmer or a meteorologist on staff to analyze and quantify this data on an ongoing basis.
Yeah, lots to be considered. It's a non-trivial effort to kind of create that. And the question is, you know, then who makes it available and accessible, who maintains and updates it? But I think for the time being, you know, understanding the use, application, and the demand, especially by civil engineers, structural engineers, is really helpful for NOAA and its scientists to grasp and grapple with, really. I have one more question coming in from my colleague, Garrett Graham. And Garrett, if you're listening, I think it'd be great if you would like to unmute and ask.
Sure thing. This was, hi, Eric. Thanks for the talk. That was awesome. This is kind of just a follow-up to, you know, bridges are heavy on our minds here in Western North Carolina because we saw a lot of the smaller ones get washed out. And while I know there is some asymmetry to how they're built to handle extreme events like this, is there any sort of, you know, bridges during flood events like this get extremely asymmetric forces, water's flowing in one direction. Is there any sort of discussion at a higher level nationally about how to asymmetrically design these bridges in order to better handle extreme forces like that, where you have all the water flowing from upstream to downstream in a flood event?
And when you say asymmetric, you mean either the strategies on different types of bridges or actually the physical bridge has something different on one side versus the other?
Either or. I was thinking more of the second one, where you actually, because we look at a bridge and I just, you know, the bridge kind of, it looks the same on the upstream side as the downstream side, at least to an untrained eye. I'm sure it probably isn't internally, but I can imagine scenarios where they look radically different on one side versus on the upstream side versus the downstream side.
Yeah, so I'll sort of answer both questions. I think they're both valuable. So on the debris side and designing one side versus the other, there have been places where they've actually put debris blockers in front of the bridge so that catches the debris and the bridge itself is not damaged. So that's one method. We've also been looking at, and this is all at the concept level, can we make breakaway railings that would be able to withstand the force of a car in one direction, but if a log were to hit it, it would actually give way so that it doesn't take the entire bridge with it if that guardrail is hit. So that's something that's sort of in the works and more of a cutting edge aspect. On the asymmetric design, sort of the level of resilience for one bridge versus another, I think one of the key ideas that the industry is working through and thinking through is this idea of resilient corridors or hardened corridors, where things like evacuation routes, key freight routes to get food and water in are hardened to a point where they can withstand just about any event that occurs. Of course, you don't want to be taking away resources from other bridges that maybe are equally necessary for other communities, but trying to prioritize, right? Because if you think of tens of thousands of bridges, even with historic levels of funding for the transportation sector, we can still only meaningfully touch and retrofit or replace a small percentage of those bridges every year based on just limited availability of people even to perform the tasks. And so there really does need to be a prioritization that's involved. And that's why I think things like rapid replaceability to be able to respond wherever the event occurs should at least be one key strategy that we're able to use.
Thank you. Looks like we've got a lot of work to do to integrate information from scientists to engineers. Eric, you have one more question coming from Jack Settlemeyer regarding your far left image, which I guess would be under prepare. Thanks, Eric. Is there a CSV file with the 624,000 bridges with lat and long locations and characteristics such as elevation above nearby terrain per state? Maybe deep within the links shared above. So I guess this would be the National Bridge Inventory location.
Yeah, let's see if I can pull up the Federal Highways performance, because that would be the place. So you can see my screen here. This is, and I'll put this into the chat as well, just so everyone has it. This is the location to look at at bridges. And this is really a testament to the work that's being done by Federal Highways to make this more amenable. If you go to data here, of course, it's not, the link is not working, which occasionally does happen. Let's see. Anyway, this is the location that you would go to. I think there might be a few other adjacent links where this could be accessed. And this allows you to look, here's an example of a map where you can actually see every bridge that's in of that 620,000. You can also look at and query them by table. This one is showing the 620,000. You can query this one, I know it's hard to see, I'm sure on your screen, by state name and pick all the bridges from a state. And I believe there is an export to CSV file among the 127 parameters for that bridge. And so it is possible to do that. There's a little bit of sort of Python cleaning you have to do. It's largely been cleaned, but there are a few minor tweaks that need to occur to make it usable and geolocated.
Eric, there's one more comment, and I know maybe you and I have talked about this before, but water.noaa.gov is another reference that we wanted to make sure that you and the rest of the engineering community and others are aware of water.noaa.gov. The National Water Center has this new experimental area hydrologic discussion for rapid flood events. So this could be a source that we bring to you or have one of our scientists sort of present either with you and your community on what is being thought of and conceived of in addition to the IPG data products. So I should mention, and with Russ being on the call here, that Erik is involved in the IPG efforts and hopefully part of the discussions with the committee and the council that's working with the IPG team, IPG standing for Industry Proving Grounds, that Russ is leading for architecture and engineering. We have a remaining 5 minutes. So for others on the call, I think I will take one more question if there is one more. And I wanted to mention first that, first I'd like to acknowledge Ellen McCrae, who is not here today and was very, very excited and also equally regrets not being able to attend. We came to learn of you, Erik, largely through the engagement efforts occurring in the Northeast because you're in her region. And for others on the call, Ellen McCrae is the Regional Climate Services Director who engages across all sectors in the Northeast, but we happen to be in some of her territory. So I just wanted to acknowledge how we came to get to know you through engagement efforts. And then also, I think the reference that you shared with how cloud access to NOAA data is game-changing the engineering application and analysis. So I look forward to hearing more coming from the community as it highlights not only the demand for cloud access, but how that will change the way NOAA makes its information content available. In addition to formats, but also the resolution, the specificity, the near real time really makes a huge difference for dashboard alerts and obviously deployment of any emergency response. So that's you're speaking to a handful of us who are listening to you coming from the Asheville and Western North Carolina region. So this is a highly sensitive topic, and we really appreciate what you've shared today. One last comment from Natalie. You could provide feedback to make it useful for y'all. Okay, so going back to water.noaa.gov. Yeah, I would say, Natalie, thanks for that. And in fact, if anything, with Erik and his company and his colleague Julie, and the amount of reach and presentation and engagement that they do across at least the Northeast, Erik makes sure that he brings NOAA with him and has kind of gotten a ribbon for NOAA, if you will, for lack of a better word, in all of those discussions, which means, across all these different stakeholders, not only is NOAA information being brought into the discussions, but, feedback, opportunities for improvement and engagement is part of Erik's messaging. But thank you. And I think in general, the cross-pollination of information coming from the science sources to the practitioners and understanding where we have opportunities for improvement is part of user engagement. So within the last, jump in.
Just one more thought on the water model side, and this is something that I've started looking into, but not deeply enough to really talk about today, is that things like the National Water Model and the flash flood guidance with the FFG, which I believe is updated on a regular basis, paired with the rainfall data could be another sort of open door for DOTs and agencies to better understand risk in their areas. And so it's something I'm certainly looking forward to thinking through in the future with all the NOAA friends that will have these conversations with me.
Thank you. All right, remaining 2 minutes. I would like to call upon Russ, if you're still here, if you'd like to offer any closing remarks.
No, Erik usually leaves me speechless, and he's done it again. But seriously, we do appreciate you spending time here doing the NCEI seminar. I think that this is really very well attended by these standards. And you just sit in this unique space between, like, practical applications and how NOAA data can really help in that context. So we really enjoy spending time with you. Thanks.
Yeah, certainly appreciate everyone, your time and attention today, talking about this obviously very critical topic for our country, and just for all the work that you're all doing to make what I'm doing here even possible.
Okay, so with that, I'd like to just say thank you all for listening and attending. This was a very heavily attended discussion. I hope to be able to bring more of these sort of practitioner level comments and presentations to our seminar series. Again, this particular webinar is recorded and it will be made available. And thank you to NCEI for allowing us to be part of your Tuesday webinar series. Have a good afternoon, all.